Howdy, my name is Kevin Garcia, and this is the final project presentation for our triple pendulum. This is group 3, and I'm working with Quinton and Harsheet. This is the team folder link where you can access all of our files, and it's open to everyone with the link.
For our project, we wanted to analyze a complex nonlinear mechanical system and land on a triple pendulum. Uh, so we investigated how to model, simulate, and generate the equations of motion for the system. Once everything was built, we compared the experimental with the simulated and used the experimental data to fine-tune our simulation to more accurately reflect real-world physics.
So a little bit more about the project physically. It's an open loop system modeling a 3-bar pendulum. And as you can see, like in this project concept, there are aluminum extrusion bars for the structure along with 3 bars, each connected using ball bearings. And these 3 bars are secured to a 3D printed mount and will be released from an initial position that kind of resembles an L. And the experimental data will be collected using Tracker, which is like an open source physics modeling program, which utilizes computer vision. And the frictional coefficient of the bars will be modeled as damping and will be fine-tuned during parameter estimation.
Here's our implementation plan. So there's 2 parts here in the mechanical part. We first decided on the dimensions and print the 3D models for the physical project. And then we built the actual prototype, and then we made adjustments as needed. And then for the simulation and experiment, we started with building the simulation on Simulink, and then we set the parameters to more closely match the physical prototype. And then finally, we derive our equations of motion. So here's our mathematical model. Starting off with the assumptions, we assumed that each link is a uniform rod. The moment of inertia for each of the rods is 1/12 ml squared. It's located at its center, which is L divided by 2. And then I define the angular positions, velocities, and accelerations, as you can see here. So we started with the equations with the torque due to gravity plus the torque from each of the ends of the link. This is the definitions of the constants and variables. And here I analyze each of the rods separately. So this is the torque due to each of the ends. And then here we substitute MXG and MYG. And then we finally got our final equations of motion, as you can see here.
So for the mechanical design, these are the main parts that we used. The structure, as mentioned before, is made out of aluminum extrusions, and each of the arms are these dog bone shaped bars that have these skateboard bearings at the end of them. The red bar is arm GH, and the blue one is arm AR, and the gray one is arm IB, which spells out Garib. They have spacers in between each of them, and the pendulum is attached to a 3D printed mount. And each of these 3 parts in blue at the bottom are taken from Thingiverse, which is a website that hosts public domain CAD files for projects like these. And we also use Tracker, which is that open source modeling tool to get the positions of each of those, the stickers, which are the orange, pink, and green stickers on each of the joint. Each of the stickers that we mentioned before have a color mask applied to them in Tracker, and Tracker then tracks each of these color blobs in each individual frame of the video. So for this experiment, over about like 25 seconds, we had roughly 1,500 frames of data that Tracker produced. And the X and Y position of the pendulum are shown in these plots here, which is directly plots the Cartesian position of each of the joints from the origin, which is the pendulum mount at the very top. Now, Tracker can also produce angular position plots, and each of these 3 plots also correspond to like the angular position of the pendulum. The top bar, as you can see, has a lot of jerky motion, which is those very sharp edges that you see in the plot. And the pink graph, which corresponds to bar IB, swings the most, which is the third joint, which is also why that waveform's amplitude is also slightly higher than each of the other 2 graphs. And for better clarity for each of these graphs, I know it's a little small to see here, please refer to the report and the presentation file itself. You can see each individual data point and each of the points that we captured.
For the simulation, the bones of each of the arms are essentially the same. It starts with a rigid transform block, then a revolute joint block, then a second rigid transform, and finally a solid block that acts as the rod. These bones essentially they're copy pasted 3 times. This setup is necessary so that each arm can be independent and adjusted by itself. Each arm's dimensions are measured from the 3D printed prototype parts and then added to the model. Each of the bearings was weighed, measuring about 11.1, give or take 0.1 grams, and their weight was added to the end of each arm with another brick solid using a rigid transfer. 2 graphs were generated with the simulation data for each arm, an XY graph and an angular position graph. The angular position data is collected by outputting the angular velocity between the mount and each arm's end. This signal is then ran through an integral block and a gain block. This setup was used instead of just pulling the angular velocity out because we had some issues with the data coming just straight from the velocity. The angular velocity is also used for parameter estimation. For link GH, as you can see, the XY plots for before and after parameter estimation are practically the same because it acts like a link to an anchored pivot. For link AR, we start to see some variance here. And for link IB, we see a much larger change after estimation. But it's also the simulation motion and the real world prototype are a lot closer together. These changes show that even like a seemingly small change to damping can have large consequences to the rest of the system.
So for parameter estimation, which is what we did, is to fine tune the frictional coefficients of the bearings. We modeled it as damping. And so this is our parameter estimation with our data, which is blue, overlaid on top of the simulation data, which is orange. And over a few iterations, MATLAB was able to optimize the simulation to roughly match the experimental data. As you can see, the measured and simulated data kind of match each other. And the angular position seems to generally follow the same path for links GH and AR, with the exception that the simulated data still has larger amplitudes and a few more spikes than the experimental data. And for the parameter estimation iterations, we had roughly 5 iterations of estimation. Now, the reason for this is because the bearing friction or the damping coefficient values were so small to begin with that even minor changes to these values would cause massive differences in the chaotic behavior of the pendulum. So even if the damping coefficients values changed by very little, the plots matched a lot more accurately after estimation.
This is our experiment video. This is actually the video that we used with Tracker to get our experimental data. In conclusion, the triple pendulum is an incredibly chaotic system whose motion changes wildly even with minor parameter tweaks. Using the Newtonian method, the equation of motions were derived, and the project simulating the triple pendulum is possible. Getting the simulation to match the real world data for very long is difficult. For some of our references, we have our Thingiverse link, which goes directly to the 3D printed model or the 3D model that we printed for our dog bones, spacers, and mount, as well as MATLAB help.
Thank you so much to the MXET faculty for allowing this project to happen.